Welcome back. We're talking about matroids. We've had a number of lectures already on their properties, and we've seen that one of the most important aspects of a matroid is this exchange property. So if I have two independent sets and one is bigger than the other, then I can augment the smaller one with an element from the larger independent set in order to get one. We're going to explore that more here, and in a little bit more detail in this lecture and the next lecture. And we're going to see that this will be very useful when we talk about an algorithm for finding a maximum size independent set in the intersection of two matroids. So let me jump into it and give the basic theorem that we need here. So the theorem says the following: we have a matroid on a ground set E with independent system I, and let B1 and B2 be bases. So in other words, they are maximum size independent sets. We've already seen that bases all have the same size. So these are our bases, and they're different. So let's take some element that is in B1 but not in B2. The theorem says that there exists a y that is in B2 not in B1 such that B1 minus x plus y and B2 minus y plus x are both bases. Okay, so if you have two bases that are distinct, you can always, for any element that's in base 1 but not in base 2, you can augment base 2 with that and then find some element to subtract so that the resulting base is independent, and vice versa for the other. So again, it's very useful to think about either a graph or a vector space so that you can put this into some context that's familiar for you. But let's see the proof of this. At least it should seem relatively plausible, but it's useful to see the details. Okay, so let's think about, we've taken x in B1 that's not in B2, and we've formed B2 plus x. Well, B2 is a base, so no matter what we add to it, it's now no longer going to be an independent set. And in particular, because B2 is a base, we know that this must have a unique circuit. Remember that a circuit is a minimal non-independent set. A unique circuit, let's call this C. And what it means is that any element in the circuit must be in the span of the other elements of the circuit, and in particular, X is in the span of C minus X. Remember, one way we define the span is through the rank function. So X being in the span of some subset U means that the rank of U is equal to the rank of U union X. So that's what this means. And since, of course, the rank of C is equal to the rank of C minus X, X is in the span. I'll just write that. Since rank of C is equal to the rank of C minus X by virtue of the fact that C is a circuit. Okay, so that means that X is certainly in the span of B1. This is B2 here, just to make sure. B1 union C minus X. And in particular, that also implies that the span of B1 union C minus X is equal to the span of B1 union C. Because the span of B1 is, the span of B1, of course, is, and this is, of course, all of E. So again, why is this true? The span of B1 is all of E. And now I'm adding C and subtracting an element of B1. That's why it's useful. It's not, we didn't know this from the start. And since X, what I subtracted, is in the span of C, then certainly the span of B1 and C is everything. But now we see that we're almost there. So this tells us that since B1 union C is everything, the span of that is everything, it means that there exists some other base, I'll call it B3, with B1 minus X is a subset of B3, and that is itself a subset of B1 union C minus X. And this is essentially the key of what we needed. Moreover, because C is the unique circuit in B2 plus X, C is the only circuit in B2 plus X, what that means is that B2 plus X minus Y has no circuit. Hence, it is a base. So these are the two parts. So we showed that B2 plus X minus Y is a base. And also we showed that B3 is a base, but B3 contains B1 minus X. So that means that B3 must contain some element of B2. So this is exactly the theorem. So this is an important foundation for what we're going to develop next. And in particular, we need some machinery that is going to be really useful for us. And this is a bipartite graph that we're going to define, a directed bipartite graph. And we can define it for any matroid, again, ground set E and independent system I. Now let's take any independent set. And for that independent set, I'm going to define a directed graph. So for this I, define a directed bipartite graph, which I'm going to call D for directed. At this point, we're only talking about a single matroid, but we're going to use this machinery and develop something similar when we're talking about the intersection of matroids. So I'll just keep this subscript here, and if I drop it, it's going to be because we're just talking about a single matroid. But for now, it's useful to remember that it depends on the matroid. And it also depends on this independent set. This is a directed graph on the ground set of the matroid, and it's going to have a set of arcs, directed arcs, A of I, that are defined as follows. So my set of arcs are going to contain Y, Z, where Y is in I and Z is in the complement of I, exactly when I minus Y plus Z is in I. So let me just draw a picture for you. We're going to use this picture a lot in the sequel. So here I'm going to draw all of the elements of the ground set. And on the left, I'm going to put the elements of my independent set. And on the right, I'll put the complement. So this is a graph that has edges that point from I to E minus I. And for there to be this edge from Y to Z, that edge signifies that I minus Y plus Z is also an independent set. So in particular, if there's something in, if this element is in the span of I minus Y, then there's no edge. Then there is no edge from Y. Okay, now let's see what we can do with this result. So what we're gonna be able to do is come up with a corollary. We're going to use this graph to come up with two interesting corollaries from of that exchange theorem that we gave a few slides ago. So the result is the following. Let's let I and J be independent sets that are of the same size. And let's call that, I'll give a name to that size, K. Then this graph, in particular the edge, the arc set A of I, contains a perfect matching. On the symmetric difference between I and J. So in other words, look at the elements that are in I but not in J, union the elements that are in J but not in I, there's going to be a matching by edges. And this is essentially, this is a corollary of the exchange theorem that we proved a few slides ago. There we essentially showed that there is an edge between one element of a base and another element of a base. Now we're saying that this is true for any two independent sets, and that there are edges among all of their nodes in the symmetric difference. So let's give this proof, and then we'll see what this corollary is saying in a picture. But the proof is essentially a repeated application of that first theorem. So again, having seen that first theorem, this should not come as a surprise. But we're going to see that we're building up machinery that is going to be useful later. So the proof is essentially by repeated application, at least in spirit. So that theorem that we're going to use dealt with bases. But I want to prove this result for arbitrary independent sets that have the same size. So I'm just going to define a new matroid that has I and J as bases. This is called truncation. So let's let M dash be the truncated matroid. I'm essentially also defining this term here. Let me write it out carefully. So what this means is that M dash is a matroid on the same ground set and with independent system I dash, where I dash is just every element of the original independent system that has cardinality at most K. And that makes I and J into bases. And you can check that all the other properties are essentially inherited from the fact that that I satisfies them, the properties of the defining properties of a matroid. So I dash is equal to all independent sets that have cardinality at most K. So in other words, now we can just assume that I and J are bases. So I and j are bases in M dash. Okay, so now we prove the corollary by induction on the number of elements that are in I but not in j. And just by virtue of the fact that I and j have the same size, this also has to equal, of course, the number of elements that are in j but not in I, which we have to assume is greater than 1, otherwise the result is trivial. So let's pick some element that is in I but not in j. And now we can apply for this element the previous theorem. So by our exchange theorem on the first slide, we know that there has to exist some element z that's in j but not in I, such that I minus y plus z is in j. I'm sorry, is independent. And also j minus z plus y is independent. And now let's let j prime equal j minus z plus y. In other words, this thing here. And now we can imply our inductive hypothesis, because now I and j prime have the number of elements that are in I but not in j prime is 1 less than the number of elements in I but not in j. So we can apply our inductive hypothesis. So by induction, the edges in A of I, these have, so this has a perfect matching. Let's give it a name. Let's call it N, on the symmetric difference of I and j dash. But now we can extend this to be a perfect matching of I symmetric difference with j just by adding in this edge that we already found, the edge yz. In other words, N union this edge yz is a perfect matching on the symmetric difference. And that's what we needed to prove. So let's draw this out just so that we can understand what this is trying to, what it's trying to say. So again, let's draw this this picture that we saw. So this is my set I, and this is what is in the ground set but not in I. And again, our picture is that we have an edge here. If I can remove this element from I and add this element from E minus I and still end up with an independent set. So that's a reminder of what A of I is. So now let's draw J. So I has 5 elements. J has to have 5 elements, and it has some overlap with, potentially some overlap with I. So let's suppose that it overlaps with these 2 elements. That means it has to have 5 minus 2 or 3 elements with which it doesn't overlap. So this is, all of this is J. And that means that these elements here are, these 6 elements are the symmetric difference of I and J. And what this corollary is asserting, basically again by repeated application through our proof by induction of that first exchange argument, is that there are some edges, and I'll just draw in some edges that obviously they don't have to be these, that form a perfect matching between the elements of I and J. And so this is our theorem. So this result is going to be particularly useful, and we're going to develop that further in the next lecture to use this graph and use matchings on this graph to prove results about independent sets and also about extending independent sets. That's how we're going to be using it in the sequel when we start talking about matroid intersection.